Okay, welcome to video series 2 on probability and statistics in Python. And this is part 1 of the second video series in probability and statistics. In this particular video, we will be actually discussing the link between conditional probability and machine learning. So what is the basic and the modern advancements in machine learning? I will show you that they all have to do a great deal with conditional probability. So let's get started with conditional probability. Before moving on, it is important to realize the importance of conditional probability, particularly in the area of machine learning. As I mentioned earlier, this is the conditional probability that most machine learning basically uses this conditional probability in almost every model. Let me give you examples how machine learning basically uses this conditional probability. Before actually describing the use of conditional probability in machine learning, let me first tell you a little bit about random variables. Random variables. Don't worry about the very short time treatment of random variables in this particular video. We have a whole section on random variables. Actually, the next section of this course is about random variables, and we will treat the random variables at length. But just to introduce here, just to show you the importance of conditional probability in machine learning, I'm just introducing the random variables. Random variables are the variables that basically different values of those variables represent different events. Actually, that's a way to convert events to numbers. Once the events are converted to numbers, then you can try out whole statistics on events using these variables. Let me give you an example. Let's say you toss two coins simultaneously. Your sample space might be this: a head, or a head tails, or tails and head, or a tail. That's a sample space. Assume that all these outcomes are equally likely. Just assume that. And which means the probability of this outcome is 1 over 4, the probability of this outcome is 1 over 4, the probability of this outcome is 1 over 4, the probability of this outcome is 1 over 4. Now, we can set a random variable or the variable of our interest to be, let's say x is our random variable. X is a variable that represents number of heads in the above experiment. Now, what are the different values that x can take? Well, x can take value 0. In that case, if x take value 0, we are referring to this outcome, because this is the outcome or the event that contains this outcome only. X can take value 1. Well, in that case, if the number of heads is 1, then we are talking about an event that contains this particular outcome and that outcome. So event containing these two outcomes. Or x can take value 2, which means we are referring to an event that contains only this outcome. So rather than writing all different kind of events, we can just figure out the area or the variable of interest for us, and we can assign different numerical values to that variable, and each of that numerical value actually represents the underlying event. Now, rather than talking about the probabilities of different events, we can talk about the probability of these random variables. What's the probability that x will take value 0? Well, that is 1 over 4. What's the probability that x will take value 1? Because x can take value 1, and that actually goes to this event and that event. So the probability of this event is 2 over 4. So the probability that random variable will take value 1 will be 2 over 4. Now, what's the probability that x will take value 2? Because that refers to a singleton event will with just this one outcome. So that is again 1/4. Yeah. So for one particular experiment, you can have a lot of random variables. One random variable may be the number of heads. Another random variable may be the number of tails. That might be another random variable y. You can have another random variable z, which is maybe, I mean, you can define whatever variables of interest you have, but each random variable, the variable is called random because when you perform an experiment, what value this x will take is random. We do not predict what the value will be there. So it can take the value 0, it can take the value 1, it can take the value 2, we do not know. So there is a randomness in prediction. So that's why they're like the experiment is called random, in the same way the variable is called random, because we do not know what will happen. What can happen, we do not have certainty for that. We will treat these random variables in detail, in full length in our next section. But here I have just introduced this to show you the power of conditional probability in machine learning. Now consider, for example, there is an experiment, and the experiment is that different people come in to a door. Let's say that's your office door. That's your office door. Okay, and there's a camera on top of that. There's a camera on top of that door, and people come here, and the door lock opens automatically if this particular person is authorized to come in or not. That application is basically that can be achieved through a face recognition application. Face recognition application. Now consider in this particular office or whatever area that is, consider only 10 people are allowed that are employees of this office or authorized or whatever. And let's say these 10 people, let's say y is a random variable that represents the identity of any person. Y is a random variable representing identity of a person that walks into the office. Because we have mentioned there are only 10 different people that are there, so the values that y can take belongs to this particular set, 1, 2, 3, 10. Let's say ID 1 means person 1, ID 2 means person 2, ID 3 means person 3, and so on. This variable is random because next time which person will walk in, we do not know that for sure. Further, assume x is a random variable that represents the face image. Later in this course, we will see this x not only a one variable, it is actually a random vector which has a lot of variables inside. But just for now, assume that this is a face image. By face, an image is simply a matrix of a lot of numbers with different patterns. What these intensity values are, let's say that is represented by x. Now, let's say we want to find out the probability that the person that is just enters now, whose image we have, let's say we have taken the image from the camera and that image value is this I. Let's say we have taken that. The camera just gives us the image and we know what are the values of x. Given the image, what is the probability? We want to find out the probability that this particular person is person 1. We need to find out that probability. So that probability, eventually, if we are able to find out that probability, that might be 0.2. We then try to find out the likelihood that the person eventually actually is the person 2. And that probability might turn out to be 0.7. And so on. I mean, and then we will pick the probability that is based on the maximum probability, and we will say, okay, this is that particular person. But see here, the whole face recognition app that relies on conditional probability you need to find out the probability of this y given the image. Similarly, if you want to find out the, for example, activity recognition, you have a video. Video is just a sequence of a lot of images. You have a video, and you need to find out in this particular video what activity is being performed. Then y will be a random variable that actually codes all different kind of activities, and x will be a random variable that will represent the video or the video data, sometimes called the features that we will see in detail in the next section. So now again, your goal is to model this probability distribution, which is again a conditional probability. So and then if you want a text to speech converter, you again have this conditional probability. In the regression problems where you want to estimate a particular kind of continuous data, for example, you need to find out the temperature given the conditions. Let's say somebody give you a lot of conditions that humidity level is this much and air pressure is this much. What do you think? What will be the temperature? If you want to predict the temperature given the rest of the variables, you can do that again. You can model that problem again as a conditional probability modeling. So although I was too fast here in this particular video, I have explained certain concepts that we will be dealing with in our future videos of the same course. But I just wanted to mention that this conditional probability that actually is extremely powerful, and classification and regression, all these kind of problems, they actually model this kind of probability law, and this kind of probability law is basically conditional probability, and that's a conditional probability whether you're working in regression or you are working in classification. At the end of the day, you are modeling this probability law. And guess what? Whether you are modeling that probability law using classical techniques like support vector machines or logistic regressions or maybe random forests or ensemble classifier, or even if you're using deep neural networks, at the end of the day, you're modeling this probability law. Although when we are dealing with these kind of deep neural networks and support vector machines, or for example, when we are dealing with logistic regression models and stuff like so, maybe we hide these kind of details. And maybe we do not realize that actually at the end of the day we are modeling a conditional probability distribution. But at the end of the day, whatever we achieved, we actually train a conditional probability law. And all the machine learning training where a neural network is being trained, random forest is being trained, a logistic regression is being trained. Support vector machine, let me change the word support vector machine to relevance vector machines, because the relevance vector machines, they have more connection to probabilistic modeling rather than support vector machines, because the support vector machines extension to multiple classes is not that straightforward in probabilistic sense. However, in relevance vector machines, which is a form of support vector machine in different assumptions, that has a probabilistic modeling and multi-class extension, and that also models again the conditional probability. So if you have heard about an application YOLO, you only look once, if you have heard about that application that models a conditional probability, if you have heard about text to speech recognition system that models a conditional probability, if you have heard about activity recognition that actually models a conditional probability, almost all the applications dealing with regression and classification, they actually have to model the conditional probability one way or the other. So I mean, although one can just go to the universe of machine learning and deep learning without realizing the fact that the underlying all the training process is basically building a conditional probability model. Without realizing that, you can just go into the machine learning universe. But it is always good to know that the roots of all these concepts, they are back in probability and statistics. So yeah, so I mean, I have used a lot of terms in this particular video, and I'm not expecting you to know all these terms already. I just wanted to mention that whatever you are going through, that is not just useless. I mean, these are the roots of all modern machine learning, probability theory, and particularly this conditional probability. We will unfold all these concepts that are explained in this video in the subsequent videos and sections. But I just wanted to introduce you the power and the applications of these concepts. These are not just I mean, the concepts are not just about rolling a die or tossing a coin. This is not just about that. Although we teach the concepts using very simple examples, but the application of concepts, they are everywhere. Everywhere in machine learning, everywhere. So, as I said, I'm not expecting any one of you to know the terms that I've spoken. For example, I've spoken a lot of terms like random vector, feature vector. I might have spoken the term support vector machine, relevance vector machine, logistic regression, deep neural networks. I've spoken these kind of terms. These are all the terms that are very common in machine learning. And I do not expect you to know all these terms right now. And that's okay, I know that. But I wanted to connect the conditional probability to these terms, because all these kind of classification and regression, oh, by the way, I have used the term classification and regression as well. They are also machine learning terms. But I just wanted to mention that these are basically the hot topics on machine learning. All these topics are hot topics. So deep neural network is really a hot topic in machine learning these days. And whether you are solving a classification problem or a regression problem using a deep neural network, you are modeling a conditional probability distribution. How amazing is that? I mean, the roots of all these kind of modern techniques in data science, they go back to probability theory. And that was the primary reason to introduce these terms right now, because you might be getting bored of why we are using the examples of a die every time, why we are tossing a coin, what we have to do with the coin, what are the real life problems in which the coin is tossed and they are interesting problems. Well, I'm using very simple examples to teach you the concepts that actually target very complicated situations. So don't worry about the coin and the dice. These are just to introduce you the concepts in easy ways, but do not think that the concept just stay with coins and dice. They go beyond and they go everywhere. Yeah, so don't worry, we will unravel these terms, particularly the regression terms and classification terms, estimations, and by the way, let me introduce one more thing in this video that might be getting messier and messier, this particular video. Let me introduce one more thing. Modeling this probability distribution, probability law, requires statistics. So for now, you might be thinking till now, where is the statistics? We are just, I mean, working with probability of this event, probability of that event, and that kind of stuff. Where is the statistics? Well, modeling of this particular probability distribution requires to come up with the patterns from the historical data, sometimes called the training data, and all those techniques, they require statistics, the understanding of data, to come up with this particular probability law for predictions. So yeah, I mean, these things are interlinked. They are really interlinked. So yeah, hold on. Very interesting things are coming. Hope to see you in the next video. In this video, we discussed basically the link between conditional probability and machine learning. In the next video, in part 2 of the same series, we will be discussing some random variables. Basically, we will be discussing the random variables that can be encountered in real data sets. So I'll be showing you the random variables and working with random variables in real data sets. What are the random variables? What's the notion of random variables in real data sets in data science? So hope to see you in the next part of this video series.